Oh man, not again. My battery died. Where am I going to get power now? There's no way I can get power around here. But it's such a sunny day. Maybe I can get power from the sun?
Indeed, the sun is a huge and reliable source of energy, but how can we convert this energy into electricity? You must have heard about solar cells, but do you know how they work? And how many of them would we need to power Mike's laptop so that he can keep playing this awesome game? First, let's take a look at a solar cell. Wow, that's really thin, and in fact, there are even two super thin layers in there. When the sunlight hits the cell, it gives enough energy for electrons to break free and travel through an external circuit generating electricity. But let's have a closer look at the cell to understand how it really works. Most solar cells are made of silicon. By themselves, the atoms of silicon would be organized in a very stable structure. However, when phosphorus atoms are added to the silicon structure, they disrupt the nice arrangement because they have one extra electron compared to silicon. This electron cannot bond to the neighboring atoms, and it becomes a free electron. If we add a lot of phosphorus in the silicon, we end up with a lot of free electrons in the structure. This arrangement is called n-type because it's going to be on the negative side. We can also add boron instead of phosphorus to the silicon. This time, the boron atoms have one less electron than what would be necessary for a nice layout. You can think of the lack of electron as a hole that would be free to travel through the structure. Therefore, adding a lot of boron atoms to the silicon will result in a lot of free holes in the structure. This arrangement is called p-type, as it's going to be on the positive side. To form a solar cell, you first need to break these two types together. At the region of contact, the extra electrons of the n-type would love to combine with the extra holes of the p-type. However, since the electrons are negative charges, the atoms they left now become positive ions. Conversely, the holes that combine with the electrons left negative ions on the p side. This difference of charges results into an electrical field between the two sides, which prevents more electrons and holes from combining with each other. In fact, new electrons trying to reach the junction are pushed back by the negative charges of the p-type, while new holes are repulsed by the positive charges of the n-type. Overall, the field acts as some kind of wall that keeps the electrons to the n side and the holes to the p side. So what happens with the sun? Well, when the light reaches the junction, it may have enough energy to break a whole electron combination. However, because of the field that has been created before, the electron is sent away towards the n side, while the hole is sent towards the p side. They can only recombine if this extra electron is collected by an external circuit connected to the p side. In that case, the electron will run through whatever electrical device that would be on the way before going back to the cell and finally recombine with the hole. Now, one cell like this only provides 1.5 watt of electrical power, which is fairly limited. So, if we need more power, well, we simply have to use more cells.
Hey Mike, here's a solar panel for you. It has 36 cells. That's enough to charge your laptop.
Awesome, I can play again. And all I need is energy from the sun. Isn't it great?
That's great indeed. And in fact, we can even power more than a laptop with solar panels if we use a lot of them. For example, this solar farm can power 600 average US homes. Wow, that's pretty big, isn't it? Awesome! So couldn't we just power the whole country with solar cells? How big would that panel be? Let's do a simple estimation. Over 1 year, this farm provides about 8 gigawatt-hours of electrical energy. For the year of 2010, the total electricity production in the US summed up to 4 million gigawatt-hours, the equivalent of 500,000 solar farms like this one. The area you would need for these farms would be about 1/9 the size of California. Hey, if that's all the area it requires, why don't we have solar panels powering everything yet? Well, as of today, there are two main limiting factors to solar panels: cost and electricity storage. Wait, you said cost? Don't you just get energy from the sun for free? That's correct, but the construction of solar cells is so expensive that even if we use them during 30 years, it would be cheaper to get that electricity from coal. However, improvements in technology and in materials will probably make solar cells more affordable in the future. Also, the electricity provided by solar cells is not available all the time. We could theoretically store the surplus of electricity during the day and use it at night, but storing these huge amounts of electricity is still complicated and expensive. These two reasons mainly explain why today only 0.04% of US electricity comes from solar cells. However, solar energy is very valuable because it is sustainable. The sun will still be shining and sending its energy to the Earth for billions of years. As new technologies appear, we will most likely be able to convert this energy into electricity for a cost that will compete with other resources. Anyway, if anything, the solar cells technology enabled Mike to keep playing his game.